5-2. Use perpendicular bisectors. By the end of today's lesson, we will be able to successfully use perpendicular bisectors to solve problems. The perpendicular bisector is a segment, ray, line, or plane that is perpendicular to a segment at its midpoint. So we're talking about a segment here, and let's just use a line here. This line bisects the segment at the segment's midpoint. And equidistance means the same distance away from two figures. And we'll talk about this a little bit more later. And concurrent means when three or more lines, rays, or segments intersect in the same point. And the point of concurrency is the point of intersection of concurrent lines, rays, or segments. And then we have circumcenter, which is the point of concurrency of three perpendicular bisectors of a triangle. And for the last three vocab terms, I will further explain this a little later. Theorem 5.2, the perpendicular bisector theorem. In a plane, if a point is on the perpendicular bisector of a segment, so we're talking about point C here, and it's located on the perpendicular bisector of the segment AB, so that AP is equal to PB, then it is equidistant from the endpoints of the segment. So we're talking about A and B here. CA will therefore be congruent to or equal to CB. So again, if line CP, this line here, is the perpendicular bisector of segment AB, so it cuts this segment into two equal segments, then this point, from this point to point A, point C to point A will be equal to point C to point B. So CA will be equal to CB. Theorem 5.3, the converse of the perpendicular bisector theorem, is the exact opposite of Theorem 5.2. In a plane, if a point, so we're talking about point D here, is equidistant from the endpoints of a segment, so we're talking about this part, DA is equal to DB, so A and B are the endpoints of the segment AB, then it lies on the perpendicular bisector of the segment. So if I extend line CP to include point D, we want to say that this theorem wants to let you know that D will be located on this line. So again, if DA is equal to DB, then point D lies on the perpendicular bisector of segment AB. Okay, let's look at an example that illustrates theorem 5.2, this one. If line AC is the perpendicular bisector of BD, so this would be, we can mark these. Find AD, we want to know the length of this. So then we can conclude that from point A, AB is equal to AD by theorem 5.2. So I can take 7x minus 6 equal to 4x. And this would be equal to 2. And since we want to know the length of AD, we need to take 4 and multiply by 2 to get 8. Example 2. In the diagram, line KN is a perpendicular bisector of segment JL. Part A. What segment lengths in the diagram are equal? Well, we can first say that NJ is congruent or equal to NL. NJ is equal to NL because line KN is a perpendicular bisector. So I'm just going to make a note here. And we can then conclude that by theorem 5.2 that KJ is equal to KL. So I'm going to write KJ is equal to KL, and I'm going to write theorem 5.2. Now, I notice that from JM and LM, they have the same lengths, and I want to know if M lies on the point, so by theorem 5.3, we can confirm that because JM equals to LM. So we can write M or MJ equals to ML. Doesn't matter. JM equal to LM or MJ equal to ML. And in part B, it asks you, is M located on line KN? And since from part A, we stated that MJ is equal to ML, then M is equidistant from J and L. So by theorem 5.3, the converse of the perpendicular bisector theorem M is on the perpendicular bisector KN. Theorem 5.4. Concurrency of perpendicular bisectors of a triangle. This theorem states that the perpendicular bisectors of a triangle intersect at a point that is equal distance from the vertices of a triangle. So what does this mean? It means that if P to F is the perpendicular bisector of segment AC, and PE is also the perpendicular bisector of BC, segment BC. So I'm going to extend these lines here. And that PD is also the perpendicular bisector of side BA of this triangle. Then this segment AF would be equal to this segment as well as for this side. Okay, and according to this theorem, it states that when these three bisectors, perpendicular bisectors of a triangle, intersect at this point, what we call the circumcenter, then it will be equidistant from the three vertices of the triangle. So 2, 3, 4, 1, 2, 3, 4. So again, if PD, PE, and PF, PD, PE, and PF are the perpendicular bisectors, then PA is equal to PB and also equal to PC. And if we use a compass and put the pointy end on the circumcenter and put the pencil end on any of the vertices of the triangle and make a loop, you'll notice that it will create a circle around the triangle, and the circle will also pass through all three vertices of this triangle. And that's why we call the intersection of the perpendicular bisector the circumcenter, meaning it makes a circle around the center of the triangle.